Okay, so it's our pleasure to have Renato Vianna, who will speak about open string quantum Lefschetz formula.
So yes, so this is joint work with Luis Diogo, Dmitry, Tonkonog. Fortunately, it's not in academia anymore, and Weiwei. So actually, I gave the first talk on this subject in 2018 on this paper, but so today I'm gonna explain a little bit why it took too long, besides the usual procrastination. Well, not the focus is not why it took too long, but in the end, I'll get a chance. What we did is slightly different than in our first approach. And well, first I'd like to explain the title that I think we kind of like come up with, like this fancy word after like this stringy type of terminology, but it's well, the name of Lefschetz comes here. Quantum Lefschetz was a formula that kind of like Givental gave it, because, well, I think he was inspired in, hopefully I'm not wrong, on Lefschetz hyperplane theory, that theorem that would relate the cohomology of hyperplane section of a projective variety. So he was so the theorem relates the explain how to obtain the cohomology of y out of the cohomology of x. And so the quantum here, it's so quantum Lefschetz formula would be a formula that would relate some sort of Gromov-Witten invariants on y with Gromov-Witten invariants on x. And this type of Gromov-Witten invariants are called gravitational descendants. And roughly, they are so a big chunk of the moduli space are related to counts of rational curves with some sort of given tangency at a point on y. And in fact, this sort of invariants will come up in our formula. They will, but the ones that come up for us, they are actually counting these sort of configurations. There is no kind of like a weird count with things on y or in x. So, but the quantum Lefschetz formula is a formula that would relate these gravitational descendants. Actually, the g function that is cook up some sort of generating function of these gravitational descendants in y and in x. And so here the open strings comes because we are actually going to be dealing with a Lagrangian inside y, right? So from like this kind of like in this stringy world, so the closest strings should move in this minimizing energy way and form holomorphic curves. And well, the strings with boundary on the Lagrangian will form holomorphic curves with boundary on the Lagrangian. So when we put open strings, we are being relating some sort of like relative Gromov-Witten count with boundary on the Lagrangian. And oh, I shouldn't use relative. Well, we know like disks with boundary on the Lagrangian. And the point is that if I have this Lagrangian here in y, I can always lift to a Lagrangian Lx inside some normal neighborhood of y in x that we know we have a symplectic model for that inside x. And this is called the Biran lift. So and for a Lagrangian, we can in a given choice of regular or most complex structure, we can build the potential function that give us the count let's say this Lagrangian in X of Maslov index 2 holomorphic disks with boundary on that Lagrangian. And so here, this number here is, say, the count of disks, if you want, passing through a fixed point that has Maslov index 2. Okay. And here one difference I point out, for me to write down the formula that I want to write, we usually, we're calling in this sort of like group ring notation, because now if I multiply two of them, I'm going to be actually summing the homology classes. I'm recording the whole, if you will, the whole homology class of my disk beta. But usually when we see formulas of the superpotential, so let me write down perhaps here, we usually consider the, say, we can evaluate T, we put T to the class beta, we actually take into account the symplectic area and perhaps the boundary of beta, right? And then if we have, we usually write also some xj will be with beta 1 up to beta n. So quite often I deal with tori, but so quite often we see the formulas with this sort of area parameter and encoding the boundary of the disks. Or if you will, some local system that is associated with the Lagrangian. Okay, anyway, so the point is that an open string quantum Lefschetz formula would be some formula that one would be able to obtain relating the superpotential of the Lagrangian Ly with the superpotential of the Lagrangian Lx. Okay? So this kind of like explain the title, and perhaps I'm gonna already sort of write down the theorem. And but not in complete detail. Let me put like this in some somewhat complicated. Let's put complicated. Setup, symplectic, and but that, let me say, which includes the following kind of somewhat familiar class of examples, where X would be Kahler and will be forced to be funnel. And so X and Y, let's put it like this. X and Y Kahler, and then yes, Y is funnel as well, because yes. This corresponds to an ample line bundle Actually, we could have it being just base 0.3 plus some sort of condition, but which should imply it's nef, not necessarily ample. But ample assured us our condition. So we need y ample and minus kx minus y to be effective. So there exists this d and also ample, correspond to an ample line bundle. And we also require that D intersects Y is not only the anti-canonical class Y, but in fact, it is Maslov index of Ly divided by 2, seen as a relative homology class of Y with respect to Ly. So in particular, we don't want it does not intersect Ly. Okay. So even though this kind of like looks a little bit familiar, it's still some conditions that perhaps are not so clear where they appear about. This you should think of us having a toric degeneration. So X should be having some toric degeneration to X0. So then perhaps you have some singularities on X0 and Y degenerating to some facet Y0 of your toric degeneration. This is the kind of setup where you would pick a Lagrangian here and then kind of lift to a Lagrangian here, and whatever is the complement of the other facets we require to be ample, and then the intersection would miss the Lagrangian, compute the should be computing the Maslov class. Okay, this is the sort of examples where actually all the examples that I can cook up come in this sort of fashion. Okay, so this is the setup. So in this setup, what we can prove is the following. The superpotential associated with the Lagrangian in X is obtained from a copy of the superpotential on Y with some sort of modification plus one count for F, that would be the fiber disk, plus some L equals to 0 or 1, I think it's 0. Or 1. 1 to infinity. Some on homology classes in X that intersects with Y L times, and then what we call the psi, I probably should get the number right, L factorial, L factorial, psi L minus 2 point, and then A minus LF. Okay. These are weird gravitational descendants. But what we can do, it's actually a consequence of, well, we have to work a little bit, but follows, we do use a lot the work of and allow me to show that in this case, this becomes L times the relative Gromov-Witten genus 0 in class A with tangency L at the point. So in other words, this coefficient here, and in this case, the Gromov-Witten also, this relative Gromov-Witten is also not counting curves inside Y. It's already compact the count of curves in class A that has tangency. And here I think the terminology of tangency, the right one is that, say, if you have some quadratic thing has tangency 1, so it generically intersecting in L points, so tangency L minus 1. And so these extra terms come from holomorphic spheres in X tangent to Y. And what do I want to say? We do have some restriction on the classes for which this guy can be non-zero, can actually get a rigid count. And so this is actually, the fact is a rigid count would imply that it intersects. So the Chern class will have to be L. You imagine, right? This would be a rigid count, would give some restriction. In the Chern class would have to be L plus 1. And from here, you would see that it would have to intersect this divisor once because it intersects Y L times. Anyway, okay, so this is the more complicated formula that we arrived in a somewhat complicated setup where we try to mimic this sort of Kahler setup and ample-based conditions that come from algebraic geometry. All right, yes.
What is WLY tilde?
Oh, yes, okay, that's next slide is a picture. I also need to tell you what is F. I'm not sure if I mentioned, but okay, you have Y here, you have your Lagrangian here, Ly, and then there is the lift Lx, this inside the neighborhood. Okay, and the point is that for each relative homology disk-like class in Y, it's actually true for every homology class, but it's a little bit more, it's nicer that we can trivialize the normal bundle over disk to show that there is a unique lift beta tilde of this class beta, for which the Maslov index of beta tilde is equal to 2. Okay? So if you force the class to project to beta and have a Maslov index 2, it's unique. So if we have the superpotential here, say,
On one option, crispy crunchy chicken on spring street.
shut up, Siri.
One moment,
Okay, where was I?
still on it.
Yeah. So, then the tilde version will be just same coefficients, but you put the beta tilde class here, right? And the F is just this fiber disk over here, because this lift is just this lift, it is in this sphere bundle of X. It's just a nice S1 fibration over Ly, and the normal fiber will give you a Maslov index 2 disk. Okay. So let me perhaps give a very simple example. This is when we are going to take the Lagrangian torus, the standard torus in CP2, and lift to the torus in CP3. So, so in this case, then the divisor Y is equal to CP2. And the potential, we can write down, of course, choosing some well, you could put perhaps you would have T to the area of the disk, whatever is the symplectic area of the disk. Say we are doing the monotone case, and then like with the right choice of bases, you're gonna have something in the 1, 0, something the 0, 1, and something then -1, -1. Okay, so this is the standard potential of torus in CP2, and then the one in CP3 is very similar. But look, note that if I kind of like I delete this guy to trivialize the bundle here, so that this X lifts to this X, this Y lifts to this Y. You see that this guy here now will lift to something that I will write like this. So this should correspond to the WL tilde. So this beta tilde, once you fix the basis for one, it may you may have to, relative to the other one, pick up some class of the fiber. And this corresponds to the fiber. So in this case here, you see that that D is perhaps some smoothing. So at least the class of D that would be smoothing of this 3CP2 is 3 times the class of CP2, and you have therefore no contribution from these relative Gromov-Witten invariants with the correct tangents condition. So there is even though the formula looks quite complicated, we actually have a bunch of examples where this formula is very simplified. One of them is when it doesn't appear. And this is actually, I'll tell you later when, but this is actually the work of Biran-Khanevski. And then there is yet a setting where this formula becomes easier. Perhaps I'll say some remark here, because here kind of like I'm assuming that we are taking the J, the integrable J, or if it's not regular, perhaps a small perturbation of it. But so in general, superpotentials, they are invariant for monotone Lagrangians, right? But we can still, on the non-monotone setting, make sense of this formula, provided we restrict ourselves to some subset of holomorphic, almost complex structures that, in this example, we would require that it maintains Y and some copies of Y, because it needs to be base point free. We need to have some copies of Y, and D also in some sort of like base point free systems of D. All of these holomorphic. So we kind of like can control bubbling and say that moving the J's, or which will be equivalent to that moving your Lagrangian without crossing these divisors, would give you the same sort of superpotential formula. Okay, so there is some sort of thing to be said what almost complex structures I'm taking.
Very nice question. In the WLX in your example, what happened to the T to the area?
Oh no, it's still there. Sorry. It's just that one thing that I forgot that I want to mention. So perhaps let me put this. So the potential is actually an invariant up to you apply a symplectomorphism of your space. You apply symplectomorphism of your space, and you I think morphism is pH, right, or not? It's pH. I start writing in Portuguese now, and then I'm doing so you do a symplectomorphism of your Lagrange of your manifold, see where it took L. It will have the same potential, of course, if you correctly identify the Monge classes according to the symplectomorphism. When L is monotone. So, does everyone here know what monotone Lagrangian is? Yes? So I do not need to. Okay, then I won't write the definition, because that saves in time.
So when you say it's invariant for when L is monotone, is that the case where we can prove it, or we have a counterexample with a non-monotone?
Yes, and when it's non-monotone, you can yes, you can you have from Clifford to the Chekhov torus, you can on say non-monotone version of the Clifford torus and non-monotone version of Chekhov torus, you can Hamiltonian isotop them and change two disks to one disk, say in C2, for instance, with the same J. Yes, there's this.
Just so I make sure, there's this L factorial times the gravitational descent, and at the bottom the factorial's gone.
No, yeah, here's just an L. Yes, there is.
All kinds of cool numerology happening here, because presumably you're doing this using tangency constraints, and those aren't gravitational descendants, we have to relate them. And
yes, yes.
is there any way that you can explain like the sort of numerology of these things in a straightforward way, like where the L factorial is coming from, where
No, not
YL minus 1
Not really,
It gets swallowed up into a relative Gromov-Witten invariant.
yeah,
All these things get very complicated and presumably.
yeah, it's something,
In your complicated setup and not in other setups. I mean, that's somehow usually the story, right? So.
right, yes. I won't remember it by head, and it's sufficiently complicated for us. I do remember we use quite some result of LLM, and then there is some sort of counts that comes when we stretch, and we have to count the cylinders in the proper way when we glue them. But it's well, it's there. The proof is there. But it's not. I don't have good intuitive.
Okay. Yeah, I was just curious.
A very good intuitive.
Means.
But there is, if you look in LLM's paper, there is some sort of proof of some sort of tangential invariant that he proves that is L minus 1 factorial times the gravitational descendant. There is this sort of result in LLM's paper. We took that result and we reinterpreted, we proved that whatever is the other thing is actually this sort of relative moment. Right. Was this this sort of idea, but I don't recall the details from the top of my head.
Just to clarify it, I mean, is this gravitational descendants or cyclas insertion from stable maps, or you pull them back from stable curves? Which one is it?
I have you integrate some sort of modular trace, this kind of like
Or these classes live on the stable map moduli space, or you pull them up along this forgetful map, which forgets the map and maps to the domain.
I don't remember. Honestly, I don't remember. I really, if I were to give the definition, I would really have to recall and study the definition, how it comes this line bundle of this modular space and the pullback with the map and integrating over the modular space. I actually have it here somewhere, but definitely I didn't put on my notation. If I was, I would believe it's the modular space of stable maps. But oh no, it's not in this one. It's in the older version. But anyway, let me try to not. I'm going to convince you now, or at least I hope to convince that this formula can become somewhat easier in the following setting. So, but before that, what was one of the main motivations that we come to this is because one of the motivations, or actually the main motivation that we started the project. Is to work in a monotone setting to distinguish use the WL to distinguish monotone Lagrangians. And well, from that, so there is a theorem of myself that up to symplectic morphisms of, if you want, Hamilton isotopy, there exists infinitely many monotone Lagrangians on del peso surface, which is known through a series of work of Macduff and some other people. These are all the monotone fourfolds. So So the closed form manifolds which are monotones, they are all the closure surface, which means that they are blow-ups of CP2 up to 8 points, or CP1 cross CP1. And so out of these infinitely many monotone Lagrangians, we can start then embedding them into some bigger space. And in this case, I want also my divisor as well as my X and Y to be both monotone and satisfies the condition of the theorem. So here is a diagram of a bunch of embeddings satisfying these sort of conditions. And then we start with this del Peso surface. And the theorem that this diagram is telling me is that if I take all these tori that I construct, and then I start lifting through this diagram. If I take two of them in the same space that I obtain from the lifts, if they have the same, not even the same potential, sorry. If well, what would imply they have the same potential? If L1 is equivalent to L2, it means it came not only from the same space, but the very same Lagrangian. Yes.
Is Q a quadric?
Q is quadrics, yes. Quadrics, cubics, sorry. So here's quadrics, here's cubics. 5 blowups is the complete intersection of 2 quadrics, sorry. Yes, quadrics, cubics, yeah, I didn't say anything about this diagram. And this is the flagged threefold. So, in other words, we not only can construct these several Lagrangians using Biran lift, but we can distinguish them. How much time do I have?
20 minutes.
20 minutes, great. So, but there are some cases which are, for instance, this here and this sort of lifts here, that I claim that perhaps I'll leave this there. That I claim that the result was actually already proven, besides some perhaps epsilon work of really write down what the lifts formulas give you. But so let me perhaps define some setting where this result was proven by Biran-Khanevski, is when we have X omega monotone, and then you have Y with omega restricted to Y also monotone, and you have Y proportional to the, also proportional to the symplectic form. Of course, I'm using Poincare duality always when I'm writing this kind of stuff. And so this Biran-Khanevski, they call this kind of like Donaldson condition. So this would be some sort of Donaldson monotone. But because this sort of condition is very far from the divisor that Donaldson would construct out of omega, that will getting people confused. So we decide to know to denote the following: if this happens, then we say that X and Y is a monotone pair. So we will introduce this notation. And then, so first thing is that I think it's in Biran-Khanevski, but could be just Biran, this one. First thing that they show is that if you have in this condition Ly contain Y monotone, so we can make in this Donaldson condition can make the neighborhood big enough for you to be able to find a lift Lx that is also monotone in X. So this is the first point, okay? That exists. And then, somewhat hidden in the Gist sequence paper for Lagrangian homology is the following theorem that using our terminology translates the following. If C1 of Y, C1Y, this is the minimal Chern number. And you only need to be true for, you could just evaluate the Chern class. I would put spherical class, but let me write the spheres. You only need to evaluate the Chern class on the spheres. If the minimum number is bigger or equal than 2, then which is, for instance, this case, then we do have that we only have the contributions of these Lefschetz disks plus the contribution of the fiber disk. Okay? And so these rows of embeddings here already satisfy this condition. And so, for instance, if you wanted to know that there is infinitely many tori in CP and out of the infinitely many tori in CP2, kind of the result is already there. So this is the first sort of like inspirational. Our main inspiration came from this sort of result, and we wanted to try to understand what happens precisely when we allow C1 of Y to be equal to 1, minimum Chern number equal to 1. And then this is when we get these extra contributions. But let's do some computation here. So in this monotone pair setting, we do have I use lambda already. Let me put sigma. We do have X monotone, Y is monotone. Put it tau of kappa. And Y is Donaldson. So in particular, we cook up this number. We can write down a junction, of course, we stick to Y, C1 of Y plus Y. But you see, Y and C1 of Y, they are proportional. This can be written like that, where Y is equals to R C1 of Y, and then this R is what? C1 of Y is tau omega, so tau is in the denominator, right? Is R equals lambda over tau, and then you can guarantee that this needs to be an integer. Okay. So so in this case, you see that forcing not only that, right? This is minus kx. Okay, this would then have to correspond to d restricted to y, and this is just y, right? Over there. So in particular, our extra contribution will come from Chern 1 classes. Okay, and then you can write down the potential. Let's perhaps leave this here. Let me erase the example. We can write down the potential. We have a simpler formula because in this case, then so this number r will only have one r here that will satisfy this condition, right? So this formula became and then if I write down t to the class of beta, so as I was saying, on the monotone case, everyone has the same area. So I can really think that I'm going to put t equals to 0, t equals to 1, because everyone has the same area. And then I kind of like just record the boundary of the class. Okay? So using this sort of notation, we will have that omega Lx becomes omega Ly tilde plus t to the boundary of y. Let me call it z. Z will be this guy to the boundary of the fiber disk. Then what I will have, so all this guy here, this t becomes z the minus L, because when I take the boundary, this has no boundary, becomes minus L, the boundary of the fiber disk. Okay, this term here, and then we get all the L's will have to become R, and then we'll get oh sorry, L is R, R G0 R XY of a point when this guy here is, you're going to be summing the classes that will intersect precisely with tangency R minus 1, well, multiplicity R. Okay, so the formula looked very complicated, but in this monotone per setting where we find a lot of examples, and most of examples, the guy that we only have one extra term essentially on the potential. Okay, it kind of like simplifies the formula a lot. And this was the fourth formula that I announced in 2018. And so now let's see the time, 10 minutes. So and so I announced the formula in 2018, and all of these examples plus well, it's also recorded in YouTube. You can see all other applications that we gave at the time. It was in a Merson conference in Berkeley. don't remember, but you can find the talk there. There are more applications. So now perhaps I'll just say something in words and then give you a glimpse of the proof, the idea of the proof. So, but what motivated us to enhance our theorem from this sort of monotone pair setup to a more complicated setup was the following result and the following thing. So first, Dmitry, during this time, he proved, it's a non-published paper, but it was correct. So he shown that that if you have a monotone Lagrangian torus, then you can recover this G series coming out of these gravitational descendants out of the superpotential. In precisely the same way that Givental proves that you recover the theory from the superpotential in the toric case. The G series from the superpotential in the toric case. So Dmitry showed that every time you have a monotone Lagrangian, you can recover this G series encoding these gravitational descendants. And then there is a work of Corti, Coates, Kasprczyk, and Galkin, where they took the theorem of Givental and worked out precisely a more precise and explicit formula in some examples. And in that example, they have this sort of condition, but the requirement that X is toric, for instance. So then we saw, but this in contrast to all these conditions regarding monotonicity, it was very kind of like a non-trivial intersection, but a very different sort of hypothesis. Then we start thinking on how to generalize our theorem. So essentially generalize to some sort of setting where we ask Y to be ample or something slightly weaker. We ask also this to be ample, which is in that paper, but also we have this sort of like relative position. You need to find the Lagrangian, this Lagrangian is some sort of relative position with this divisor in this satisfying this sort of hypothesis. And well, when you can find this setting, is slightly more generic than toric. I think when you have toric degenerations like that, so kind of like we can think that we are generalizing this toric assumption to something, but if it's not coming from this sort of toric degenerations, I don't think it's that easy. As we know, it's not, if you're, so Donaldson tell you how to cook up divisors precisely in the class of omega. But to cook up some divisors on the anti-canonical divisor to make a Lagrangian, an anti-canonical divisor do not intersect the Lagrangian is hard, much less to ensure that it has this sort of relative condition. So cook up these divisors may be a priori difficult for a given Lagrangian. Okay, so this is the motivation, and let me try to say in 5 minutes the idea of the proof. What's the main idea behind the proof is the following. We are gonna, so first, as was actually shown by Biran-Khanevski, if you only look at the neighborhood of the Lagrangian, we already see these terms, the fiber disk and a natural potential that will lift. Okay. And then you do next stretching on the boundary. And then when you do next stretching, using these sort of conditions, you see that the only thing that can happen is here outside, here you have your divisor D, and strongly using that it intersects D. Well, you know when you do next stretching on this normal boundary, you know what are the red orbits. And the only thing that can happen is you have some sort of like arc over of a cylinder. And this is kind of like the configuration that under the hypothesis proof is the only possible one. It breaks into trivial cylinder times and a disk upstairs, only one disk. All the other disks will have to intersect D, and you prove that this is the case. Then you relate this to the tangency to this sort of count by gluing to this one are copies of the fiber. And then when you glue these things, you have this kind of count. And of course, you also do next stretching to show that this sort of counts will have to, in this case, break in this way. Okay, so this is philosophically how the invariants, how these extra terms come out. Okay, then we need Lam's paper also to relate this to the descendants. Okay, and do I have more time?
2-3 minutes.
2-3 minutes. Okay, good. So there are some other applications that we do. For instance, let me say one verbally. We have this sort of like Hori-Vafa potential that comes from for hypersurface up to degree n of CPN. And one thing that we are able to show is that using this sort of formula, we were able to prove that this potential does actually arise as some superpotential of a Lagrangian on these hypersurfaces. And well, in this case, we are able to cook up this side because this side would be some sort of a mutation from the superpotential of the Clifford torus in CPN, would be one mutation away. And this, oh, I guess in CPN there is no contributions like that, even for the hypersurface, or perhaps, well, I'll have to think a little bit. But then we knew this. I think we don't have this, and then we were able to cook up what is this one would be the Hori-Vafa potential. So sometimes this formula is as in these diagrams. Usually we would know this. We would be able to somehow keep track of that and understand this one better. But sometimes, I mean, there is three kind of like, well, this formula is easier. There is like three things that are unknown. Sometimes you know two of them and discover what's the third. And finally, there is one example that is slightly interesting because it gets out of this sort of monocompare setting, which is you look CP2 times CP1, and then I usually draw the triangles on the side, and I draw it different than my usual thing. But so here, the smoothing of a copy of this CP2 with this P1 times P1 give us a reasonable surface. It's kind of like smoothing of this. And so my Y would be my my reasonable surface, and then you and the Lagrangian that I'm going to take will be this Lagrangian torus here with these disks. But then notice that, so there is this X, and then if you want an omega to make X monotone, let me call the standard omega here omega 1 and here omega 2. So for X to be monotone, I think we need to take 2 times omega 1 plus 3 times the class, the symplectic for omega 2. Of course, I'm taking the pullback under the projection and so on and so forth. But then to Y to become monotone, you would have to take so this I think it's like this. It's 1 omega 1 plus 2 omega 2 if I recall well. And because the class so Y Donaldson, so Y is the sum of this guy with this guy, and so this is omega 1 plus omega 2, right? So you don't have we don't have this monotone pair condition, but somehow one could think that change these coefficients, we still maintain the form Kahler, right? With the same J, it would work, and then we can somehow change the coefficients, can be thought of as some sort of inflation along the divisors. So we can be modifying the shape of them and start, say, with the Lagrangian that's monotone for this symplectic form here, leave to some Lagrangian Lx that after you deform will become monotone for this symplectic form there. And then you can relate the potentials of them. But you can, in this setting, can still apply our formula to relate this potential of them. Okay? This gets a little bit out of this monotone pair setting. And I'll finish here.
Questions?
So I understand the next stretching argument, which you kind of gestured at. So the fact that it's tangency r-1 means like when you stretch the neck, it just winds around this fiber some number of times. And for some reason, that's a minus sign instead of a plus sign because of orientations of the divisor, the symplectic form of the divisor. And then that's sort of the idea of the argument. And then this L times something is because L times this other thing is supposed to count some more geometric object.
Yes,
we
actually counted the geometric object, and we proved that in this setting will be equal to the descendants, right? And then the L here has to do to when we have this kind of like multiple cover that you want to glue together with these disks that's wrapping R times L times here in the boundary. There is some sort of like different say choices for the gluing. There is some sort of when you quotient out by the model space, you're still left out with L possible choices of gluing that will glue in
because it's an L-fold covered orbit.
It's an L-fold.
That's why.
Yes, that's an L-fold.
It's this like annoying SMT. Okay.
Yes. So there is kind of where the L comes from. And well, the point here is also understanding right the possible break-ins that we can have, but then we use strongly that we have this divisor here that control the intersection of the class. Yes.
So maybe any last. So LX, is it monotone in your complicated symplectic?
So no, it's not necessarily monotone.
So this thing is not an invariant.
It's not an invariant, but
In some class.
yes, we choose we choose some say we choose some J's to compute the potential, and we have some restrictions on this J. The restrictions that we have is that it's gonna make our divisors holomorphic, but not only our divisors. We make some choices of like these emptiness imply this sort of like base point free. So we need to have some several copies of the divisor such that the intersection of all this DI is eventually non-zero, to make sure that we don't have anything sticking up inside one of them. So we force them all to, so we are working in a restricted set of J's that will force this sort of several divisors here and several copies of we also need some copies of the divisor Y to control things not bubbling off inside Y.
The normal bundle should be trivial.
No.
And how can the divisors not intersect?
So two of them intersect, but if we take a sufficient number of copies of them, big copies of them, yes. So yeah, this is sort of like these base point free conditions that we need to from them to have, and then we in our complicated setting we need to rephrase what ample means, and rephrasing what ample means would be having to get some sort of yet another sort of symplectic divisors and so on and so forth. And then, but the point is, we work with the J's that will make all this collection of divisors holomorphic. It's a non-empty set, and it's sufficient, and also is sufficiently generic for regularity. And the point is that in this setting, there is we control bubbling. There's no Maslov index 0 disk bubbling, for instance. So for the J's varying in this setting, it becomes an invariant for varying these J's, which can be translated into it being invariant for me varying the Lagrangians, but not crossing these divisors.
And
But perhaps let me say one thing else. Once we know this sort of potential, it's something that was already expected and talked about but it is in my work with Egor and with Dmitry that we actually proved that if you look to the minimal area disks when they are not monotone, this is still an invariant, and we still can cook up some interesting properties out of them. So being able to compute one and relate to some potential in the other, you can still say something. Yes. You had another.
do you have a conjecture for the general formula?
No, I think we don't know what happens, for instance, if we allow churn zero, the presence of churn zero spheres and things like that. No, I don't think. Yeah, and we definitely can cook up some. Yeah, we may think about that, how to generalize it, but no, not for now.
More questions? If not, thanks Renato again.